Hello everyone, this is chapter 4.2, and in 4.2 we're going to be covering the subject of nomenclature, and this is about naming of compounds. So let's get started. This lecture consists of one video, and the learning outcomes are on display on this screen. Feel free to pause the video and resume once you have read them. The slide will move on after 5 seconds. There are millions of organic compounds in existence today, but as chemists were discovering these compounds, it became obvious that some of these compounds were isomers of other compounds, and this necessitated a systematic nomenclature system to be developed. Just as each distinct compound has a unique molecular structure which can be designated by a structural formula, then each compound needed a characteristic and unique name. As organic chemistry grew and developed, many compounds were just given trivial names, and some of which you may recognize, like methane, or butane, or acetone, or even ethyl alcohol. But these common names often have their origin just in the history of science and the natural sources of these compounds. The relationships of these names to each other is arbitrary, and there's no rational or systematic principles that underlie their assignment. The IUPAC, which is the International Union of Pure and Applied Chemistry, brought about a systematic approach to nomenclature. And it did so by doing two things. First, the compound being named should indicate the number of carbon atoms in that compound that are bonded together in a characteristic lattice of either a chain or a ring. Second, it should identify and locate any functional groups that are present in the molecule. Here we see a table that contains the most common organic functional groups, and you'll notice that there is a priority assigned to them. The reason that they have a priority is because what if you had two functional groups within the same molecule? Then a system was devised such that one group gets the priority. Hence, this is the suffix that's given to the name of that molecule. Therefore, if there are any other functional groups, these are given prefixes. Now, you might be wondering what this is based on, and in essence, it's an arbitrary agreement by the IUPAC, although note that there is some correlation between the oxidation state of the carbon and the priority. In other words, more oxidized groups tend to get a higher priority. Let's take a look at some other functional groups within this priority list that sometimes cause students a confusion. This table is a summary of the functional group nomenclatures, but it includes the alkenes, alkynes, and alkanes. These are sometimes a source of confusion for students, particularly the alkene versus alkyne, and which takes priority. This really depends on what you mean by the word priority. For the purposes of a name, "ene" becomes before "eine" alphabetically. So when an alkene and an alkyne are present in the same molecule, then the ending will always be "eine", that's Y-N-E. For the purposes of numbering, if there is a tie between an alkene and an alkyne for determining the lowest locant, now a locant is just the name given to the position of a particular functional group, then it will be the alkene that takes priority. There are some functional groups, however, that have no priority whatsoever, and these are always going to be prefixes. So these have been deemed, if you like, unworthy of ever getting their own suffixes. So here are some of those here. You'll notice right at the bottom of the list we have the ethers and the alkyl halides. This list is now extended to include the following. On the next slide, let's have a look at some common alkyl groups that you will encounter, as these are accepted by IUPAC and can be used in the name of a compound. Organic chemists, when they report their work in the literature, often make use of reaction schemes like this. So notice that there is a common theme occurring. There's an R an R1, an R2, R3, and that these are conserved in the product R, R2, and R3. Now the R groups represent an alkyl group, and an alkyl group is a molecular residue, hence R, that is obtained by removing a hydrogen atom from a hydrocarbon. So here we see a table of this. If we have the hydrocarbon methane and remove any of those hydrogens, we get an alkyl group structure. And an alkyl group in this case is the methyl group, and it's given the common abbreviation Me. You notice that I may have referred to this in earlier lectures. For ethane, if we remove a hydrogen atom, we get the ethyl group, and this is Et. For propane, we now have a choice of removing a hydrogen from the terminal atoms or from the middle atom. If we remove a hydrogen from the terminal atom, we get a propyl group. But if we remove a hydrogen from the internal atom, then we get the isopropyl group. Then we move up to butane, we get N-butyl and sec-butyl. Then you can see the same thing, we have 2-methyl propane, whereby there is a methyl group attached to that central carbon, and this becomes isobutyl or tert-butyl. Benzene is often shortened to a phenyl group and is represented by the abbreviation PH. So that now we have an idea of when you see R groups, and that these are often used in IUPAC names, let's actually take a look at what's in a name. There are three parts to any organic molecule's name. There's a prefix, which includes the substituents or any minor functional groups. So if you have, for example, an alkane and it has some of those R groups as branches, then this is what we mean by substituents. If, however, you have a functional group that is a lower priority than the main functional group, then again, whether they are branches, that is substituents, or minor functional groups, a locant will be used to indicate where they are within the molecule. And this is just a number. Now that number will be relative to the parent chain. And the parent chain or ring size tells you how many carbon atoms there are in either that chain or that ring. In addition to this part of the name, if your molecule contains multiple bonds, like for argument's sake an alkene and an alkyne, then notice in the multiple bond index that you have the final E in brackets. Now you drop the final E if there is a functional group like an alkene or an alkyne that is part of the parent chain. Finally, you have the functional group, the main functional group, as the suffix, and again you have to use the priority table in order to designate which one is the main functional group within the molecule. Also note that we number from that carbon first. Anyway, a little bit more on that later on. Let's take a look now at an exemplar organic molecule and these features again. Here's an organic molecule and its associated name, and I've referenced the previous slide using the same colours as before. So the blue indicates the prefix, and the substituent in this case is a methyl group, and the minor functional group is an amino group because the carboxylic acid has a higher priority. Now the parent is represented in black, and the parent chain is 5 carbons, and we number the carbons from the main functional group, which happens to be the carboxylic acid. The carboxylic acid ends oic acid, and this is the suffix of the name. There are 2 numbers in this particular molecule, and the 2 numbers reference the position of the amino group and the methyl group. Now they just so happen to be in alphabetical order, but if they weren't in alphabetical order, you would alphabetize these. The locants, as I mentioned earlier, represent the carbon atoms that bear the amine group. So the amino group is on carbon number 2 of the parent chain, and the methyl group is on carbon number 4 of the parent chain. There are some more nuances applied to each part of the name. Let's take a look at each of these nuances in turn. The first place to start in a name is actually with the parent chain, and this is the longest carbon chain that contains a functional group. So, for example, we have 4-methylheptane, and notice that the methyl group is on carbon number 4, irrespective of whether we start from the left and number to the right, or whether we start from the right and number towards the left. For 2-propyl-1-pentanol, however, the number 1 that you designate is determined by the main functional group, which in this case is the alcohol, as indicated by the suffix -ol. So therefore the carbon that bears the alcohol is given the number 1, and then we identify the longest possible chain. So we number from right to left, and we end up with a 5-carbon chain. Note we don't call this pent-ol, it's very awkward and doesn't roll off the tongue. We normally say pentanol, so we introduce that extra syllable when naming. Alkyl groups have to be smaller carbon chains than the parent group, and also we try to give them the lowest possible number with respect to the parent chain as well. Let's have a look now at the suffix, which is the major functional group. There are 2 molecules on this slide. Both have a different functional group. See if you can try and name both of these molecules. Pause the video and press play when you think you have an answer. The first molecule contains a carboxylic acid, and so this is the primary functional group. The parent chain is numbered from this group 1, 2, 3, 4. This makes this butanoic acid. So note it's not butoic acid, it's butanoic acid. So we always include that extra syllable. The second compound actually has a substituent. And like before, we need to identify the principal functional group. The principal functional group is highlighted in red, and this is an amide. Hence the suffix is amide. And when we number the carbon chain, we number from the carbonyl carbon of the amide from the right to the left of this molecule. This means then that the substituent, the methyl group, is at the 3 position. It's incorrect to number the carbon chain from 1 to 4 the other way round. Let's have a look at some minor functional groups now. So not all functional groups are created equally. Here we have some minor functional groups, and these will always be prefixes. They will never appear at the end of a name. The alkane in the first molecule is a propane because the longest carbon chain is 3 carbons long. Now we also try to ensure that even if there are minor functional groups, that these get the lowest locants. And so the lowest possible locant has the chain starting at 1, where the carbon bears the bromine, all the way to 3 for one of those methyl groups, as indicated here. So this molecule would be called 1-bromo-2-methylpropane. And again, we also try to ensure that these minor functional groups are presented in an alphabetical order. So the other molecule, that's nitroethane. The ethane is the black bond that you see between carbons 1 and 2, and then the nitrogen is that of the nitro group. Students often mistakenly add an additional carbon here. The blue bond is always going to be joined to the atom that is a minor functional group. The position of the functional group from the end of the chain, as we've talked about on previous slides, indicates where the substituents are. So remember, you have to number the longest chain, that's the parent, from start to finish. Have a go by completing these two examples. Pause the video and press play when you're ready to resume. The first example is a ketone, and here we have 5 carbons in our longest chain. So we number these to give the ketone group the lowest possible priority. Hence this is 2-pentanone. Or you could call this pentan-2-one. However, you definitely can't call this 4-pentanone because this would give our major functional group a higher locant number. The other example is the acid heptanoic acid, and remember the carbon chain starts from the carbonyl of the carboxylic acid, and so we number out from the longest chain as indicated in black. So the methyl group is at position 5, hence this becomes 5-methyl heptanoic acid. Not only do prefixes indicate the names of the alkyl substituents and or minor functional groups, but these can also indicate the number of these groups that are present in a molecule. For example, the common prefixes used in nomenclature of inorganic compounds, you may have heard of 2 already, would be carbon monoxide and carbon dioxide. The mono prefix is not often used in organic chemistry, but all of the other prefixes can be used. Let's have a look at an example molecule. The one on the left is labelled as 2,2,5-trimethyl-heptane. The heptane contains the 7-membered parent carbon chain, and the 2,2,5 indicates the locant of those methyl groups. So there are 3 methyl groups in total, hence the prefix tri. In addition to this, the locants are chosen so that they are the lowest possible numbers. Let's now consider the second molecule. When the parent chain has both a halo and an alkyl substituent attached to it, we number the chain from the end nearer the first substituent, regardless of whether it is a halo or alkyl group. If 2 substituents are at an equal distance from the end of the chain, then we number the chain from the end nearer the substituent that has alphabetical precedence. Well, in this case we can't do that because there's actually a point of difference. Now the point of difference is between the methyl and the chlorine group, but there's a point of difference at the free position, and therefore the dimethyl group gets the locants 2,3 and not 7,8. Therefore the correct use of locants for this molecule would be 8-chloro 2-methyl-nonane. There's just a couple more things to consider concerning the use of prefixes. Let's take a look at an example now. Firstly, when we have 2 functional groups within the same molecule, we need to decide which is the major and which is the minor. So you have a table for doing that, and it was presented earlier in this video. The carboxylic acid gets the suffix because this is a higher priority group than the alcohol. Therefore, for the alcohol functional group, we now use a prefix to indicate that this is a minor functional group within the molecule. It becomes hydroxy. When we label the parent carbon chain, we label from the carbonyl of the carboxylic acid because this is our main functional group. So we number from left to right in this instance. When applying the locants to this, we need to ensure that we do so in the alphabetical order. So hydroxy does become before dimethyl because the di is ignored in the nomenclature system. So it is 5-hydroxy and 2,2-dimethyl pentanoic acid. So that's the first molecule. The second molecule, we now have a situation where we have major functional groups, minor functional groups, and also different multiple bonds within the parent chain. So let's see how this works. As before, the major functional group is the carboxylic acid, so we number from this end with respect to any other functional groups. So 1, 2, 3, 4, 5, 6, and 6 is our hex part of the parent chain. So now what needs to happen is that the locants are applied. So we have 2-methyl, 4-oxo. Oxo is used when the ketone is not the main functional group, and this is in fact a minor functional group. The multiple bonds are now concatenated or joined up with the parent chain. So we need the locant, so it becomes hex and then 2-enoic acid. And the En, remember from the earlier slide, we said we drop the E, and this is exactly what we've done here. So this is 2-methyl, 4-oxo, hex 2-enoic acid. So multiple bonds will be combined with the parent. The last thing is the order in which you present the minor functional groups and the substituents. This has to be alphabetized. This last example includes one final nuance, and that is what to do if the amino group is substituted by an alkyl group. So, firstly, please try to identify the major and minor functional groups within this molecule. Pause the video. When you think you have an answer, please resume. Okay, so the major functional group within this molecule is the carboxylic acid. So this will end enoic acid. The minor functional groups are the alcohol and the amino group. Now, when it comes to naming this molecule, we still need to identify the parent carbon chain. And this is, well, that's over to you. How many carbons make up the parent chain? Pause the video and resume when you have an answer. If you said 5, then well done. This is in fact a pentanoic acid molecule. Now we need to decide what to do about the minor substituents. As I said before, the amino group has an alkyl substituent. This is a methyl amino group, and so therefore we combine this and place it into brackets. And this is treated then as being one functional group that contains a substituent. Now we have the hydroxy group. This is at position 3. So we don't do this in order of locants, we do this in alphabetical order. So hydroxy comes before 2-methylamino. So the full name of this molecule would be 3-hydroxy 2-methylamino, which is placed into parentheses, pentanoic acid. It would not be 2-methylamino 3-hydroxy pentanoic acid. Let's consider one final example whereby you have a molecule that has the prefix cyclo near the parent chain. What do you think that means? Well, let's take a look. We're going to try to draw the structure for 4-ethyl 3-hydroxy cyclohexanone. Well, the cyclohexane indicates that this is a cycloalkane. So the parent is the polygon that is a hexagon. So this would be our parent. We know that the suffix is -one, so therefore this is a ketone. The next thing to do is to place the alkyl substituent relative to our main functional group. So we'll put the ketone at the top and then number the carbons going around. This is 1, 2, 3, 4. So the ethyl is at the 4 position and the hydroxy is at the 3 position as indicated here. And this is the same for all of the cycloalkane groups. Here is your first pre-lecture task for nomenclature. This is the only pre-lecture task for chapter 4.2. Please see Canvas for details of its submission. In the next lecture, that's lecture 4.3, we're going to start looking at conformational analysis of alkanes and cycloalkanes. Join me there.